Hello everyone, I'm Sanjeev and I welcome all of you to second presentation in the phase second of reinforcement learning channel. So the topic of this presentation is least square policy iteration algorithm, which is an off policy algorithm. So let us begin with the overview of least square policy iteration algorithm. So least square policy iteration or LSPI basically extends the idea behind the LSTD to control problems. LSTD can be applied to the prediction problems, and LSTD algorithm has several problems. It needs new set of samples for each new policy, whereas LSPI algorithm circumvents this problem, and we will see it later in this presentation. So LSPI basically extends the idea behind the LSTD algorithm to the control problems. It uses an algorithm which is known as the LSQ or LSTDQ. It is named as LSTDQ because it's quite similar to the LSTD algorithm, and we will see this in this presentation. LSPI accepts the samples from any random policy, therefore this is an off policy algorithm. The problem with the LSTD algorithm is that it needs a new samples for each new policy, and those samples need to be collected using the policy for which you want to evaluate the value function, whereas LSPI algorithm circumvents this problem. It accepts samples from any random policy, therefore it's an offline algorithm. And the fourth point is that the samples, okay, this I already mentioned, the samples don't need to be collected in the policy for which you want to compute the value function. So LSPI basically accepts the samples from any random policy and doesn't need the samples to be collected from the policy for which you want to compute the value function. So let us begin with the theory, and the first is the Markov decision process. So MDP is a vital part of reinforcement learning, and I have explained MDP in several lectures, so I will go through MDP very quickly, and if you want to understand MDP in more details, you can refer to previous lectures. So an MDP is a 5-tuple SAPR gamma, where S is a set of all states or the state space. A is a set of all actions that an agent can take in a particular state. P is a Markovian transition model, or basically the transition probability, and its element PASS prime is defined as PASS prime, which is the probability of making transition to state S prime when taking action A in state S. That is when agent takes an action A in state S, then the probability of making transition to state S prime is given by PASS prime. R is a reward function, where RASS prime is the immediate reward when an agent takes an action A in state S and makes a transition to state S prime. The reward received in this process is the reward RASS prime, or the immediate reward, and gamma is the discount factor. So here's a control problem. So for a control problem, the target is to determine an optimal control policy. Suppose you have a task, you have several actions, you have say 5 possible actions in a particular state, and you want to determine what is the best possible action that you can take in that state. So the optimal policy gives you the best possible action that you can take in a particular state. So the target for a control problem is to find an optimal policy for a given domain, and pi is a mapping from states to action. That is, if the policy is a deterministic policy, then it will basically assign each action to a particular state. But if the policy is not deterministic policy, then it will assign the probability of taking particular action A in a state S, and this is denoted by pi S comma A is basically the probability of selecting action in a state S. If pi is an optimal policy, then it will give the best possible action, and by pi S we denote the action that agent takes in state S. That is, the pi s defines the agent's action in state S. Pi s comma a defines the probability of taking action A in state S. So here comes the state action value function. I will go through this very quickly as it has been discussed several times. You can refer to previous lectures in case you have any doubt. So q pi s comma a is our state action value function with the expected discount total reward when taking action A in a state S and thereafter following policy pi. That is, the state action value function for state action pair S comma A is defined as the expected discounted total reward when agent takes action A in a state S and makes a transition to next state S prime, and from S prime it starts following the policy pi. So this is known as the state action value function for a policy pi for a particular state action pair S comma A. Every state action value function or the state value function satisfies the Bellman equation. So the Bellman equation for state action value function is defined as q by s comma a is r s comma a, where r is some reward function plus gamma, which is a discount factor, gamma times sum over all s prime p a s s prime times q pi s prime comma pi s prime, where pi s prime is again the action that agent takes in state S prime. This denotes the action taken by this policy in state S prime. And here the reward function r s comma a is defined as sum over all s prime p a s s prime times r a s s prime. This is quite simple, and this has already been discussed in previous lectures, this equation for state action value function. So the above equation is same as this can again be written in this form. That is, the state action value function is the expected discounted total reward when agent takes an action A in a state S, makes a transition to a next state, and thereafter follows the policy pi. Therefore the expectation is taken over the policy pi. It is the expected total discounted reward that agent gets when it takes action A in a state S, makes a transition to a new state, and thereafter follows the policy pi. Here the gamma denotes the discount factor, and which can be recursively written as q pi s comma a is basically the expectation over the policy pi of rt plus 1. That is the immediate reward for taking action A, that is at in a state S, that is st, and making a transition to a new state st plus 1, plus gamma times q pi s t plus 1 comma a t plus 1. So this can be written in this form. So in the matrix format, the Bellman equation can be written as q pi is r plus gamma times p pi q pi, where p pi, that is pi, denotes the dependence on the policy pi. So here q pi and r are column vector with mod s times mod a components, and p pi is a stochastic matrix of dimension mod s times mod a cross mod s times mod a. It defines the transition probability from state action pair S comma a to state action pair S prime comma pi S prime. That is, it represents the probability that the agent will take an action A in state S and will make a transition to state S prime and will select the action given by the policy pi, that is the pi S prime, the action taken by policy pi in state S prime. So the p pi, that is a stochastic matrix, its element represents the transition probability of making transition from state action pair S comma a to state action pair S prime comma pi S prime. So here's a control policy. For every domain, or we can say for every MDP, there exists a unique policy which is known as a optimal policy that maximizes the expected discounted return of every state. There is optimal policy pi denoted as pi star, maximizes the expected discounted return, or we can say it gives the best possible action in a given state. That is, if you want to know what is the best possible action in a given state, you just follow the optimal policy and it will give you the best possible action in every state. And policy iteration is an algorithm for finding this optimal policy pi star. It does this in a recursive manner. It first identifies the value function for given policy pi, any policy pi. It finds the value function corresponding to that policy, and then it makes the next policy, that is say policy pi plus, as a greedy with respect to the value function of the previous policy. So suppose you have a policy pi 1, then the policy iteration algorithm computes the value function for the policy pi 1, and then it makes the policy pi 2 greedy with respect to the value function of the policy pi 1. So in this way, the policy iteration algorithm computes the optimal policy for any MDP. So here is a quick review of policy iteration algorithm. As I mentioned, the first step is the value determination step. At this step, say in an algorithm, the present iteration is iteration number t, and you have the policy pi t. So the value determination step will first identify the value function for this policy pi t, which is denoted as q pi t s comma a. There is a state action value function for a given state action pair s comma a for policy pi t. That once this state action value function is determined, the next step is a policy improvement step. At this step, the policy improvement step makes the next policy pi t plus 1 greedy with respect to the state action value function of policy pi t. What this means is that for each state, the policy improvement step will assign the action that will give the maximum reward in that state. So the policy pi t plus 1 is greedy with respect to the state action value function of the previous policy. So by repeating these two steps, that is the value determination step and policy improvement step, the policy iteration algorithm identifies the optimal policy for a given MDP or a given domain. So these steps are repeated until some convergence criterion is satisfied. So here comes the value function approximation, and I've already mentioned the value function approximation in the previous lecture. There is a least square temporal difference learning. So here's a review of the value function approximation. You have the value function which is known as q pi s comma a, and it is approximated using the linear function approximation. This vector, this phi represents the basis function for representing the state action pair, where phi is a mapping for a state action pair to a vector in Rk. So phi and w are column vector with k components. That is, we have k basis function for representing the state action pair, and for each component, each of the k component, we have a particular weight which is defined by the components of this weight vector w. So this phi s comma a transpose w determines the value or the state action value function for the state action pair s comma a. And in the matrix form, this can be written as q as phi times w. So this was a very quick overview of the value function approximation, and you can refer to lecture number 1 for details. So here comes the fixed point solution, and this LSPI algorithm and LSTD algorithm basically solves for the fixed point solution. In the LSTD lecture, I had not discussed the fixed point solution. I have just mentioned that it computes the fixed point solution, but here we will see what fixed point solution is. So the Bellman equation for the state action value function in the matrix form is given as q pi is equals to r plus gamma times p pi q pi, where p pi denotes the dependence of this stochastic matrix on the policy pi. And using a value function approximation, this q pi is represented as phi times w. So it gives phi times w is equals to r plus gamma times p pi phi w. So to find the fixed point solution, our target is to find the fixed point solution. Basically, we will see that the least square methods solves for the fixed point solution. So let us now understand the fixed points estimate of the state action value function. So suppose this blue plane, this plane or hyperplane represents a span of matrix phi. That is, the all possible linear combination of the columns of this matrix phi represents this span of this matrix phi, and it is represented by this hyperplane. So phi times w this q pi, which is represented as phi times w, there's a linear combination of the columns of this matrix phi will be on this hyperplane, because this hyperplane represents the all possible linear combination of the columns of the matrix phi, and phi times w is nothing but a certain linear combination of the columns of matrix phi defined by the weight vector w. So this phi times w will lie on this hyperplane. So the first step is to apply the Bellman operator. Bellman operator is equivalent to one step transition, and for a particular policy pi it is represented as t pi. So applying the Bellman operator to this value function takes it out of this hyperplane. It doesn't need to lie on this hyperplane. So this Bellman operator is in general a non-linear operator, and therefore applying the Bellman operator to the value function will take it out of the span of the matrix phi. So applying Bellman operator gives r plus gamma times p pi times phi of w, which is equivalent to one step transition. The next step is to bring this thing back on this hyperplane. So we need a projection matrix that projects this t pi q pi back on this hyperplane. So here's a projection matrix, and it's given by phi times phi transpose phi inverse phi transpose. So multiplying this PR pi with t pi q pi will bring back this on the hyperplane, because this is a projection matrix, and the projection matrix will project the result on this hyperplane. So after applying this PR pi to t pi q pi, we'll bring back this on this hyperplane, and once it gets in this hyperplane, then again any linear combination of the columns of the matrix phi can represent this value, this PR pi t pi q pi, because it lies on this hyperplane or the span of phi. So there must be a certain linear combination of the columns of this matrix phi that represent this value or this vector. So therefore the fixed point solution finds the weight vector such that phi times w is equivalent to PR pi times the Bellman operator applied to the value function phi times w. So this is the overall picture of the fixed point estimate of the value function. Let me repeat this once again. You have this hyperplane that represents a span of matrix phi, and therefore phi times w will be on this hyperplane. But applying the Bellman operator means taking it out of the hyperplane. Say this represents the value, and once we apply the Bellman operator to this value, it will take this value out of the hyperplane. So what we do, we project this back on the hyperplane using the projection matrix. So we pre-multiply this t pi q pi with the PR pi, which is a projection matrix, and this brings the result back on this hyperplane. And now once this comes on this hyperplane, it means it is in the span of matrix phi, and therefore there must be a certain linear combination of the columns of the matrix phi such that phi times w is PR pi times t pi q pi, or t pi phi of w or q pi. And therefore the fixed point solution tries to find this weight vector w such that the two things are equal, the two vectors are equal. Phi times w is equal to PR pi times t pi of phi w. So this is the overall picture of fixed point estimate of the state action value function q pi. So in mathematical terms, this is equivalent to phi of w is equals to PR pi times t pi of phi of w applied to phi of w, the value function, and representing this PR pi using the equation gives phi times phi transpose phi inverse phi transpose r plus gamma times p pi phi w is equal to phi of w. So here we get the solution for weight vector w, and w is given as phi transpose phi minus gamma times p pi phi inverse phi transpose r. So this is a theoretical solution for the weight vector w when the transition matrix, this stochastic matrix, is known and the reward function is known. But in general, in practical problems, it is very hard to determine the transition probability or this stochastic matrix and the reward function. And therefore to implement this LSPI algorithm, we use samples to identify this weight vector W. So this is the end of the theoretical part of this presentation, and now we'll begin with the practical implementation of the LSPI algorithm. So enough theory, and now we'll begin with the practical solution of this algorithm. So as I have mentioned in theoretical section, we have seen that R and P pi were known. There is a stochastic matrix or the transition matrix or the Markovian transition model, and the reward function were known. But in real world problems, these are not known. So this is not the case with real world problems. No transition model P pi or the expected reward model R is available, and therefore the samples are used. The samples for the LSPI can be collected using any random policy, and for LSTD algorithm, as we have seen in the first lecture, the LSTD algorithm required the samples from the particular policy pi for which the value function was to be computed. But this is not the case with LSPI, and there is a plus point for the LSPI, and therefore samples from any random policy are accepted. So for LSPI algorithm, particularly for LSPI algorithm, we need the data that are in the form of tuples of st, at, rt plus 1 and st plus 1. We need the state st, the action taken in state st represented by at, the reward received when taking action at in state st and making a transition to state st plus 1, there is a reward rt plus 1, and the next state st plus 1. We don't need the next action at plus 1 as it was required in the LSTD algorithm. We just need these four elements st, at, rt plus 1 and st plus 1, where rt plus 1 is the reward when agent makes a transition to state st plus 1 by taking action at in state st. So here comes the learning algorithm of the LSPI algorithm, which is named as LSQ or LSTDQ because it is quite similar to the LSTD algorithm. So the solution for the weight vector W is of the form A times W is equal to B. There is a theoretical solution for the weight vector W, as we have seen. Weight vector W is given by phi transpose phi minus gamma times P pi phi whole inverse times phi transpose R. So it can be represented as solving a linear equation, that is A times W is equals to B, where A is given by phi transpose phi minus gamma times P pi times phi, and B is given as phi transpose R, phi transpose times R. So as we know in the real in the real problem, this reward vector R and the transition matrix P pi are not known, and therefore A matrix and B vector cannot be computed a priori. So therefore we need some approximation method to approximate this matrix A and the vector B. So this is not gamma times P pi phi, this is just P pi phi. We will approximate the matrix phi, the reward vector R, and P pi times phi, but not gamma times P pi times phi. So we want to approximate the matrix phi, the reward vector R, and P pi times phi, and we'll approximate them using the samples. So say we have a tuple of samples, that is Si, Ai, Ri, Si prime. Please note here the change of notation. In general, we denote the reward received when taking action AI in state Si as Ri plus 1, but here I am representing it as Ri and not Ri plus 1. So we have n set of tuples and each tuple define a particular element Si, Ai, Ri, and Si prime. There is the next state when agent takes action AI in a state Si. So we have n such tuples, and the original matrix phi is given as phi s1 comma a1 transpose up to phi s mod s comma a mod a transpose, that is the all possible combination of state action pair. The length of this is mod s times mod a, that is quite large if the domain is a continuous domain. If the domain is discrete domain, that is, if you have say 20 states and 2 possible action, then mod s times mod a is just 40. But if you have a continuous domain, then mod s times mod a is basically undefined, because there can be infinite number of states. And therefore we approximate this matrix phi with the samples. The phi is represented as phi s1 comma a1 transpose, phi up to phi sn comma an transpose. Using the tuples, we define phi for each state action pair. So the next thing is to approximate the matrix p pi times phi and the reward vector r. The exact representation of p pi phi is given by this vector, and as we have seen, the length is going to be infinite in case of continuous domain, because the length is mod s times mod a, and in a continuous domain problem there can be infinite number of states. So apart from having the infinite length, we actually don't know this matrix p. We don't know what p s1 comma s1 a1 and s prime is. If we know the transition matrix, we can easily solve this problem, but in real problem we don't know the transition matrix. So apart from having the problem of infinite length of this vector, we actually don't know the matrix p, and therefore the exact representation is not possible. And therefore we approximate this matrix with the samples that we have collected. So we approximate it as phi of s1 prime comma pi s1 prime. So for this first tuple, that is s1 a1 r1 and s1 prime, we select the state s1 prime, that is when agent takes an action a1 in state s1, it makes a transition to state s1 prime. And to approximate the p pi times phi, we use the state s1 prime, and we use the current policy, that is the policy which is currently active, for which you want to compute the value function. We use that policy to compute the next action, to estimate the next action that the agent can select in state s prime. So use the policy pi for selecting the action in state s prime. We approximate the matrix p pi times phi, which is given as phi times s1 prime comma pi s1 prime transpose up to phi sn prime comma pi sn prime transpose, where we have n tuples, and therefore the length of this matrix is equivalent to the number of tuples. The next thing is to approximate the reward vector r, and as we can see, the length is going to be infinite, and apart from the infinite length, we don't know the exact value of p s1 a1 and s prime, and therefore the exact representation of this matrix is or this vector is impossible. And therefore we approximate this reward function r with the rewards that we have collected as samples. So we have n tuples, and each tuple has a particular reward r, and using those rewards we can form this reward vector, this reward function, which is given by r1 ri up to rn. So the length is going to be n. So we have approximated the matrix phi, we have approximated the matrix p pi times phi, and we have approximated the reward vector r. So LSQ algorithm or the LSTDQ algorithm approximates the matrix phi, approximates the matrix p pi times phi, and approximates the reward vector r, and we denote it as phi cap p pi times phi cap and phi and r cap. So now A matrix is going to be phi cap transpose phi cap minus gamma times p pi times phi whole cap, and B vector is going to be phi cap transpose r cap. So these are the approximations for the matrix A and vector B, and now we can solve the system of linear equation, that is A times vector W pi is going to be B, and therefore the vector W pi is given as A inverse B, and the value function Q pi is then given by phi cap times W. So this is the LSTDQ algorithm for determining the state action value function for a given policy pi. This term p pi times phi cap is dependent on the policy pi because it uses the policy pi, that is the current policy for which we want to evaluate the state action value function. That is, it uses this policy to compute the next action, that is action that the agent can take in state S1 prime. Say we have first tuple S1 A1 R1 and S1 prime, then the first element is going to be phi S1 comma A1 transpose of this matrix phi, and the first element of this p pi times phi cap is going to be phi S1 prime comma pi S1 prime transpose. That is, we don't use the exact action for the next state in the tuple. That is, say we have S1 A1 R1 and S1 prime. The S1 prime is going to be basically S2, and the agent, and then we will have certain action A2, but instead of using A2 we use this policy pi to compute the action in state S1 prime, and this step basically makes this LSPI algorithm independent of the policy used to compute the samples. Therefore, this step makes this algorithm an off policy algorithm, and therefore it can use the samples generated using any kind of policy, any random policy. So this step is the innovation in the LSPI algorithm or the LSTDQ algorithm, and basically, as we can see, it is quite similar to the LSTD algorithm with a slight modification, or the main innovation that makes this algorithm an off policy algorithm. This pi S1 prime represents the action taken by the policy for which you want to evaluate the value function. This policy gives the next action, and actions are taken according to the policy for which you want to compute the state action value function. And this step is the innovation in the LSPI algorithm over the LSTD. This step circumvents the need to collect new samples for each new policy. Therefore, LSPI can accept samples from any random policy. So here's the LSPI algorithm. We have two steps. One is a policy determination step, which uses the LSTDQ algorithm to compute the state action value function. Once the state action value function is computed, the policy improvement function makes the next policy greedy with respect to the state action value function of previous policy. So suppose epsilon is any stopping criterion. We have n plus 1 tuples, and here we are using the exact representation, that is st at rt plus 1 and st plus 1. We have n plus 1 such tuples. We form the matrix B. B is given as some over t from 0 to n phi of st comma at times rt plus 1. And once we compute this vector B, we enter the policy iteration phase. We can fix the maximum number of iterations. In general, it is 20 or 15. We compute the matrix A, and then we find the weight vector W, which is given as A inverse B, and then we make the policy pi I greedy with respect to the state action value function of previous policy. And then the next step is that if this difference is less than epsilon, there is a stopping criterion, then this algorithm will stop and it will return the weight vector W. And if it is if the convergence is not achieved, then this algorithm will terminate once the maximum iterations are over. So this is the overall algorithm, LSPI algorithm. You can find it in the publication of Professor Ronald Parr, and I have mentioned the link on the web page of the course ARL. So the overall picture is that LSPI circumvents the need to collect the new samples for each new policy, and therefore it's an off policy algorithm. It uses the samples from any random policy, and therefore it's a data efficient algorithm because you don't ignore the data collected using the previous policy. You can gather data from any random policy, and then you can use all the data to compute the value function for a given policy. So here's an example on the chain walk domain. A chain walk is a 20 state chain walk domain. You can find the details of chain walk domain in several publications. It's a discrete problem. It has two possible action, left and right, and the actions have the probability of 0.9 to produce a desired result, and with probability 0.1 they produce the opposite result. The two possible actions are to move left or left and right. That's to move left or right in a particular state. The reward is 1 only in the state number 1 and 20, and is 0 everywhere else. So the optimal policy is to move left in state 1 to 10 and move right in state 11 to 20. And here's the policy found by the LSPI algorithm. And so I'm collecting the samples with 100 episodes, and each episode has a limit of the maximum number of steps as 50. So once I have collected the samples, I can initiate the LSPI algorithm. I'm using the discount factor of 0.9, and I'm using the value of epsilon as 10 to the power negative 6, and the maximum number of iterations are 15. So LSPI converged in 3 iterations. LSPI took 3 iterations to converge, and as we can see, it has found the optimal policy. That is, to the blue action, the blue represents the left action and red represents the right action. And this is the value function. It represents that red, that is the right action, is favored in states 11 to 20, and blue, that is the left action, is favored in states 1 to 10. So the next domain is the Acrobot domain. I'm not going to discuss the details of this domain. You can find the details in several publications. Just to remind you, it's a continuous domain problem. So here's the result of running the LSPI algorithm with the proto-value functions. You can choose any kind of basis function. The basis functions phi can represent either the polynomial based function, they can represent the Fourier basis functions, they can represent the proto-value functions. So for Acrobot domain, I am using the proto-value functions with 35 proto-value functions, and using the LSPI algorithm, and this red represents the result of proto-value function with SPP algorithm. I will explain the SPP algorithm in the upcoming lectures. In this lecture, this is the graph. The blue graph represents the result of running LSPI algorithm with the proto-value functions, 35 proto-value functions, with proto-value functions as the basis functions for the Acrobot domain. And let me show you the practical working of this Acrobot domain. So here I am using number of episodes. I am using 20 episodes, and each episode has maximum steps of 1000. So this algorithm will repeat twice. So I am setting it to just one loop. So first it will run for 20 episodes and then it will run for 21 episodes, with each episode having 1000 maximum steps allowed. So it's collecting it's collecting samples using 20 episodes and 1000 steps in each episode. Maximum steps are 1000. It's generating the proto value functions, and then the LSPI algorithm will solve the policy iteration problem. So the success was achieved in 128 steps for 20 episodes. And likewise we can see for 21 episodes. So the overall idea is that in Acrobot domain you have to achieve a certain angle with the two arms, and you have to achieve in as less number of steps as you can. So as we can see, with increasing number of episodes, the number of steps for achieving the goal is decreasing, which is good. And with 50 episodes, the average number of steps is around 75 or something. Sorry, is around 100 or something. So this experiment was carried out with 50 repetitions for each episode. So thank you for watching this presentation. I am Sanjeev from searchingeye.com. Thank you.